Hello, I'm Nazgol Nikravesh. I will explain what we did in our paper in this presentation. If you look at the title of our paper, you will understand it is about cross-project defect prediction. And we used an enhanced transfer boosting algorithm to solve this problem. A growing number of software projects makes it increasingly crucial to predict software defects. A common way to reach this goal is using within-project defect prediction, or WPDP. But these models need sufficient labeled data of the same project. So there is a question: what if sufficient labeled data is not available? In this situation, we should use cross-project defect prediction, or CPDP. In these models, training data are from source projects, previous mature projects. The test data are from target projects. As you understood, the training and test data are from different projects, so they have different distributions. Cross-project defect prediction often reduces distribution differences by either selecting training data or using transfer learning methods. Using transfer learning effectively reduces distribution differences in recent CPDP models, yet none of them have taken into account the possibility that negative transfer may occur as a result of the imbalanced nature of defect data. In this paper, a 4-step model is proposed, of which 3 steps are dedicated to the preparing the training data and their initial weights for use on the 4th step. The 4th step involves an enhanced version of the transfer boosting algorithm. Therefore, aside from reducing distribution discrepancy between source and target data, this model also addresses the issues related to defect data class imbalance. The prediction performance results of our model were consistent and accurate. We tested our model on 15 projects from 3 famous and publicly available repositories, and the improvements by our model were more than 5% in some datasets in the case of AUC and FMeasure. Finding defects is costly during the test phase, and STP addressed this issue by predicting defects in the earlier phases. As we said earlier, WPDP requires sufficient set of labeled data from the same project, which is usually not available in early phases of software development's life cycle. So CPDP is the proper option here. The most important point here is that CPDP should address distribution differences and WPDP-related challenges like class imbalance problem at the same time. When CPDP models use transfer learning methods, a potential problem is occurring negative transfer. It means the deterioration of CPDP performance due to the effects of unrelated or less related source instances. TRADA-Boost is one of the most widely used algorithms in CPDP models, but it has several shortcomings, like there is no mechanism for regaining source instance weight in later boost iterations. Its source weight updating strategy only increases the weight difference between source instances and target instances. In order to deal with this problem, ray transfer algorithm is proposed. Recently, more and more CPDP techniques have been investigated. CPDP techniques can be divided to 2 approaches generally. First, source data selection means selecting source instances or source projects based on their similarity to target data. The second approach is using transfer learning algorithms. TL algorithms used in CPDP are from two approaches: instance-based transfer learning, feature-based transfer learning. In the case of instance-based, using Tiara Boost and some newer versions of this algorithm is popular in CPDP. For example, iTiara Boost used Tiara Boost algorithm with some changes which makes it suitable for CPDP characteristics. In our paper, we used ray transfer, which is an instance-based transfer learning algorithm. In the case of feature-based transfer learning, one of the most famous approach in CPDP is TCA+. This model combined normalization data and TCA algorithm, in which source and target projects are mapped to a common latent space based on their distribution distance. Model is a mixed project defect prediction in abbreviation MPDP model, which is a subcategory of cross-project defect prediction. This kind of model is used when we have a very limited labeled target data and we can use that besides the source data. Our model consists of 4 steps. First step, NN filter. Previous studies indicated that utilizing raw cross-project data directly would result in higher false alarm rates due to the inclusion of irrelevant samples. So we used NN filtered, which is based on KNN, to select instances. NN filter and its efficiency were evaluated by a number of previous CPDP studies. Second step, smooth. The nature of defect data is imbalance, and the ratio of defective to non-defective modules is generally very low. To address this challenge, we used smooth, one of the most popular oversampling method. The third step, gravitation laws-based weights initialization. Ray transfer, which is used in next step, needs initial weights of training data. So we need to initialize weights in wisely manner. Weight initialization based on gravitation Newton's law is one of the methods which applied to CPDP several times. The fourth and last step, ray transfer. In this step, we used an enhanced version of Tiara Boost, named ray transfer. Tiara Boost is a transfer learning method based on AdaBoost. In this algorithm, the strategy of target weight updating is same as AdaBoost. But in the case of source data weight updating, it uses different strategy. In this strategy, the source instances which are classified incorrectly in the previous iterations get lower weights. In ray transfer, a label-dependent cost factor is introduced, which prevents disappearing the effect of source instances, especially the defective instances, which is more vulnerable to get wrong labels. We named our model NSGRT. This name is got from first letters of each 4 steps. Here you can see the pseudocode for NSGRT. In the green boxes, you can see how label-dependent cost factor is defined and how it used in our first step model. We used 15 publicly available datasets from 3 repositories, which are from 3 different companies: ICCKE, Promise or NASA, and SoftLab. In our experiments, we chose one project as test data and the others in the same company were used as the source data. We repeated the experiments 20 times and reported the mean results. AUC and F measure are used as evaluation measures. These two are most popular performance measures in CPDP studies. For parameter settings, T in rare transfer and N in NN filter are set to 20 and 10 respectively based on previous studies. Our benchmark methods are divided to two categories. First category is state-of-the-art CPDP methods. We used four methods here: DTB, double transfer boosting, hybrid model reconstruction approach, TCS boost, transfer cost sensitive boosting, MLD, manual DOM. The second category of our benchmark methods are for investigating the impact of each first three steps of our proposed method NSGRT. So we built three new models: SGRT, NGRT, and NSGRT. As you can see, in each model we omitted one step from the three first steps. This table contains the result of our experiments, which indicates NSGRT, the proposed model of this study, generally outperformed other CPDP state-of-the-art models. As you can see in NASA or PROMIS repository, NSGRT got results which are comparable to other benchmarks, but in two other repositories, NSGRT was significantly performed better than the others, and especially in the case of average of the results. In the case of AUC, NSGRT performed very promising and outperformed benchmarks in 60% of tested datasets. In some datasets like AR4, the improvement was significant and up to 6% in AUC by NSGRT. One of the challenges of CPDP model is the stability of their results, which means the differences among results across different datasets are high. As it is shown in this table, NSGRT is more stable and its performance results are greater or near 60% in all datasets in the case of AUC. In order to the analysis of the effect of each step of training data preparation, it can be said that due to the lower average of result of NSRT in both AUC and F measure compared to the other two methods, SGRT and NGRT in general, the gravitation Newton's law-based weighting has a better effect on improving performance, since the removal of it had a more negative effect on average. It is important to note that this effect is different across datasets. For example, the removal of a smooth was more detrimental for ML and EQ. The proposed model in this study, NSGRT, addressed the challenges of CPDP, especially the challenge of occurring negative transfer because of imbalanced distribution of data. The results were promising and outperformed other state-of-the-art CPDP models in most cases and in average. As future work, we plan to use process metrics and applying other transfer learning methods to improve the performance of the model in the datasets which the NSGRT did not outperform some of the benchmarks. Thanks for attending.